prove the mean value theorem for definite integrals. So the mean value theorem for definite integrals says if little f is continuous on the closed interval ab, then you're guaranteed a value c in the interval ab with f of x equal to the average value. So in other words, f of c is 1 over b minus a, integral a to b f of x. Or another way to think about it is you can look at the value of the definite integral being the average times the length of the interval b minus a. Now the big power tools that come into this, we've got ourselves the intermediate value theorem, which says that if little f is continuous on an interval containing a and b, then intermediate outputs, values between f of a and f of b, comes from intermediate inputs, a number between a and b. We're also going to use the extreme value theorem, which says that if f is continuous, then f is going to achieve its maximum and minimum. And then preservation of order for the integrals. Okay? So let's see how this shakes out. So once again, we have a conditional statement. So we have an if f is continuous on the interval ab. So we're going to assume this. We're going to assume that f is continuous on the interval ab. That unlocks the extreme value theorem. So by the extreme value theorem, there are values. I'm going to call it x1 and x2 in the interval AB somewhere, maybe inside the interval, maybe at the endpoints, who knows, so that f of x1 is the minimum of f. So I'll write f of x1 over here is less than or equal to f of x, and f of x2 is the maximum. Okay, so we can think of this, this is the minimum value, which is a number, and this is the maximum value, which is a number. Okay, so now what I'm going to do is I'm going to integrate through, I'm going to integrate each piece of this inequality. And because of preservation of order, I know that the integral from a to b of f of x1 dx will be less than or equal to the integral from a to b of f of x dx, which will be less than or equal to the integral from a to b f of x2 dx. It's preservation of order. Now, it's really important for you to remember that the minimum here is a number, aka this is a constant. The maximum is a number, aka a constant. And so if you integrate from a to b a constant dx, you just get that constant times b minus a. You can think about that geometrically. We're literally finding the area under a horizontal line. Okay, so it's just going to be that constant times the width of the rectangle. Or if you wanted to, we do have fundamental theorem of calculus, the first part. You would have that constant times x evaluated from x equals a to x equals b. You can get it there. Either way, here's what we get. We get f of x1 times b minus a is less than or equal to the integral from a to b f of x dx is less than or equal to f of x2 times the integral of b minus a. And now I'm going to divide through the inequality by b minus a. And since b minus a is a positive number, I don't need to worry about flipping any of the inequalities. So I get f of x1 is less than or equal to 1 over b minus a integral a to b f of x dx, which is less than or equal to f of x2. So look at what I've got here, folks. I've got f of x1 and f of x2 are two outputs from a continuous function on a closed bounded interval. And I've got a number between those two outputs. So 1 over b minus a integral a to b f of x dx is an intermediate output from this function. So now I can hit it with the intermediate value theorem. So by the IVT, since f is continuous, that's what we're assuming, there is at least one value c between x1 and x2 with f of c equaling that intermediate value. And folks, there it is. That's the mean value theorem for integrals, courtesy of the extreme value theorem and the intermediate value theorem. So that'll do it for that proof.